Hi, Mr. Fauzi. We are from Group 8. So today, me and my group mates will present about the production of methanol. So my name is Ng Yi Hui, 1001747314. So this is a poster which contains objective, background, scope of work, methodology, introduction, discussion, result, conclusion, and reference. So now I will pass to my group mate for further explain about the content of this poster.
Hi sir, I'm Su Jianye, student ID 10017475444. Methanol synthesis is a widely studied process and the product methanol is commonly utilized as a fuel, a solvent, an energy storage medium, and a feedstock in the industry. This industrial methanol production process with synthesis gas includes three production steps: production of synthesis gas, conversion of the synthesis gas into methanol, and distillation of the reactant effluent. Process unit operations such as valve, heater, cooler, compressor, liquid vapor extractor, heat exchanger, equilibrium reactor, and distillation column are included in this production process. Most methanol is made from synthesis gas, which contain hydrogen, nitrogen, carbon monoxide, carbon dioxide, methane, and water. Catalytic conversion of hydrogen and carbon monoxide from synthesis gas into methanol can be done with conventional gas phase process or with a liquid methanol process. The following reactions are reactions of interest that included in this methanol production process that you can refer from the scope of work. All three reactions are highly exothermic. The conventional gas phase process carry out the conversion in reactor at high pressure. Substantial process gas recycle of hydrogen-rich gas moderates the temperature rise across the adiabatic reactor. Carbon monoxide concentration at the reactor inlet is normally limited to about 10 to 15% after dilution with recycled hydrogen. There are three objectives that could achieve from this project. First, 100 MT of methanol that could be produced per year from the syngas. Second, to design a simulation of methanol that includes reactor, separator, cooler, heater, and recycle stream. Third, total annual of carbon dioxide emission that could be reduced while reusing hydrogen stream to dilute. And next, I will pass to Yi Hui for his further speech. Thank you.
Hi, Mr. Fauzi. It's Yi Hui here again. So I will take over the methodology part. So this is the process flow diagram of the production of methanol. So this process flow diagram, or PFD, is simulated by using UNICEF with the version of R471. So now I will open the UNICEF. Okay. So the unit operation that involved in this methanol production includes a compressor, a cooler, mixer, heat exchanger, heater, equilibrium reactor, separator, and also distillation column. So in order to produce 100 megatons per year of methanol, some assumption is made through this process. So the operating condition for inlet stream are assumed with temperature of 75 degrees Celsius, pressure of 50 bar, molar flow rate of 1 times 10 to the 8 kg mole per hour. Okay, so the composition for the inlet stream for hydrogen is 0.676. Okay, nitrogen 0.003, carbon monoxide 0.23, carbon dioxide 0.066, methane 0.021, and water 0.0023. Okay. So throughout the simulation, stream 25 will be the product stream for the process which contain most of the methanol. So the mole fraction for methanol is, in this stream is 0.99, so it's around 1 lah. Okay, so the maximum rate obtained for the stream 25 for methanol is 1.163 times 10 to the power 7. Okay, so by doing the unit conversion, we can get the mass flow rate for the methanol in this stream is 101.88 megaton per year, which achieve the objective of the production. Okay, next. Okay, so now I pass to next.
Hi, Mr. Fauzi. My name is Hossein Lok. My student ID is 1001850522. I'll be taking over for discussion. So in order to obtain the desired product of 100 megatons per year of methanol, the unit operation is out as shown in the methodology. By setting the right inlet stream, we are able to synthesize the desired amount of methanol in the outlet stream. The fluid package we use in this simulation is Pan Robinson. The reason for using Pan Robinson is because it is mostly used by researchers to predict several pure components such as liquid and gas molar volumes for hydrocarbons. The two major equations involved in this process is as shown in the slide. The first one is by reacting carbon monoxide with hydrogen gas to form methanol. And the second one is by reacting carbon dioxide with hydrogen gas to form methanol and water. Next. Uh, so the inlet stream is set up as shown by my teammates in methodology. So at first, the inlet stream is directed into the first compressor when the pressure of the inlet stream was increased from 5,000 kilopascal to 7,500 kilopascal. It is then sent into a cooler to cool down the inlet stream down from 133.1 degrees Celsius to 70 degrees Celsius in order to remain low temperature for the process. A second compressor was used to further increase the pressure of the stream from 7,500 kilopascal to 12,000 kilopascal. The inlet stream was further sent into the mixer to be mixed with the recycle stream from the two separators and distillation column in order to reduce cost and waste. Next.
Hello, Mr. Fauzi. My name is Yo Yong Xiang and my student ID is 1001746787. I will continue to explain the following functions for the simulation, for the unit operations that are present in this simulation. So after passing through the mixer, the boiled water reactor, after passing through the mixer, it will pass through the shell and tube heat exchanger. So this shell and tube heat exchanger, which is an isothermal exchanger, where catalysts are installed at the tube side and the shell side is used for cooling purpose by providing boiling water. So after passing through the boiled water reactor, it will pass through the heater. So this heater is actually used to increase temperature of the inlet feed from 150 degrees to 165 degrees so that the desired temperature of the reaction can be achieved. So after passing through the heater, it will reach the equilibrium reactor. So this equilibrium reactor is actually used to convert carbon dioxide to methanol as liquid product, and it also helps to maximize methanol production. Next. So after passing through the equilibrium reactor, it will reach these two separators. So these two separators are actually used to separate syngas part living at the top of the separator from liquid methanol and water part living at the bottom. So both of the separators also helps to increase the efficiency of the separation process. After passing through these separators, it will reach the final distillation column. So this distillation column is used to separate mixtures depends on volatility. So methanol with low volatility exits at the top stream, while water with higher volatility exits at the bottom stream. Next. For the proposal of findings, both of the reactions are adiabatic, and unreacted syngases are recycled and mixed again with the inlet feed in order to save costs and reduce waste. At the end of the whole process, the amount of methanol produced and extracted at the top stream of the distillation column is 101.88 megaton per year. So this has fulfilled the objectives of this process. Next.
Hello, sir. I'm Kailun, and my student ID is 1001850251. And now I'm going to share about the result and calculation of this case study, which is the production of the methanol. Next. So this is our final simulation design about the production of methanol, and we have done through it with the unison design which has shown previously by Yihui. Next. And the following one is the details of each stream, which included the important parameters, which is the temperature, pressure, mass flow rate, molar flow rate, and etc. Next. So this is the composition of each chemical components at each of the stream. Next. So right now, we are using the separator V100 as our reactor to study about the mass balance and energy balance. We know that the mass flow rate of the inner stream must be equal to the mass flow rate of the outer stream. So for this reactor, there's 2.174 times 10 power of 10 kilogram per hour of flow rate at inlet, while the outlet is 2.166 times 10 power of 10 and 8.249 times 10 power of 7 kilogram per hour respectively. So after the conclusion, we prove that this separator is valid and working properly. Next. Meanwhile, since this unit operation is a separator, so no heat energy changes and the temperature is remain unchanged. So there's no energy balance for us to study here. Next. So for the outlet of methanol is focused at the stream 25, and all of this is the details of the reactor over there. Next. Lastly, the output of the methanol is in unit of kilogram per hour. The required unit is in megaton per year. So after the unit conversion, we can get that the output of methanol is about 101.88 megaton per year. So I'm now passing my speech to Kenye.
In conclusion, three objectives could be reached as 100 MT of methanol that could be produced per year from the syngas shown in the plant-wide simulation, and there are not any carbon monoxide and carbon dioxide gases produced in the product stream 25. Methanol production by carbon dioxide can help increasing the environmental sustainability of the process, decreasing the carbon dioxide emission and suitable methanol production rate and high selectivity. This is the end of our presentation. Thank you and have a nice day.
Thank you.